Thank you for registering to the webinar. And first of all, we would like to inform you that this webinar is going to be recorded as part of the STEAM3 project, just for you to know. If you have any question during the webinar, you could ask either through the question and answer button that you have, the chat, or just raising your hand. We will stop Jose Antonio when there is a question in order that he can answer. There will be also some time at the end of the webinar for the question. First of all, I would like also to thank Jose Antonio for the opportunity of giving us this so interesting webinar. And I know he has worked a lot and doing a big effort for having this online webinar, and just let you the time for you to go on with the webinar. Thank you, Jose Antonio.
You're welcome. Okay, so I'm going to okay. Is it okay, Susana?
Yeah, it's okay. Everything fine.
Okay, so welcome everyone for coming. It's a pleasure for me to be here with all of you through the new technologies. And it's also a pleasure for me to speak this subject that is very dear to me: electron crystallography, matrix crystallography, and computers. Okay, so what is the objective of this seminar? The objective of this seminar, we are going to, for one side, we are going to explain some theory about some basics, fundamentals about electron and matrix crystallography, basis vector, metric tensor, dynamical diffraction. And at the same time, we are going to apply all these concepts in a software, TempServer software, projections, modeling, and other issues. So we are going to mix the theory with the applications. And for the people who are interested, this book, Donald Sands, Vector Intentions in Crystallography, is very well recommended. Okay. So what is crystallography? We can say that crystallography is a mathematical language. It allows us to describe structure, crystal structure, and also to start doing a lot of chemistry, and we can predict a lot of chemical and physical properties. But this is like a mathematical language for us. And crystallography is also fun, because when we know this language, we can make very complex structure, and we can try to simulate, to modulate what we see in the electron microscope or in another subject in science. And I would like to speak a little bit about the vector space. So the first thing, or we can say that the core of the crystallography is to understand that in a unit cell, the three vectors A, B, C, also called A1, A2, A3, define a basis. And I can represent the position of the atoms in the unit cell and in the crystal by a vector with three components. So I will have a vector that has three components and three basis vector. And we can say that this defines a linear vector space in the crystal. So I can do everything defining vectors, modulus, angles. And maybe the core of matrix crystallography is this tensor, what is called the metric tensor. Metric tensor happens when I want to do a scalar product between two vectors, U and V. Each time I want to create a scalar product, I have this outer product between the basis vector. This outer product is what is called metric tensor. is a matrix 3 by 3, all the information about the crystal to measure in the crystal. So we can say that the metric tensor is the core. Once I know the metric tensor crystal, I can calculate very easy the volume of the unit cell, but I can calculate modules of vectors. As I will say distance, and I also can calculate angles. I can calculate bonding angles, so on. So I can put numbers into the crystal. So metric tensor is like a gem in matrix crystallography. But we are not only working with real space, we also work with reciprocal space. What is reciprocal space? Okay, if I have some periodicity, like these trees in a road, I had two ways to express this periodicity. One way is to say a distance. Okay, this tree and this other tree are separated by a kilometers by one tree. That will be one way to express periodicity. Another way is to speak about spatial frequency. I will say, okay, I have one tree each a kilometer. I am giving the same information. In the first case, the basis will be A, and I will say that this is a covariant basis. In the second case, when I speak about spatial frequency, the basis will be the inverse, the reciprocal. It's called B, and this is a contravariant basis. So real space and reciprocal space are like the two faces of the same coin. If I increase the basis, of course, the contravariant coordinates is lower and the covariant coordinate will be higher. So these two spaces express the same thing, but in a reciprocal relation, with a reciprocal relation. And we can say that B and A, the outer product of B and A will be the identity, because A will be the reciprocal of B and B the reciprocal of A. Of course, this is in one dimensions. I only have one dimension. What's happening when in crystal? Where are the spatial frequency? The spatial frequency will be the family planes. The family plane will be that I find in a crystal will be the spatial frequency that I represent in the reciprocal space. For family plane, I can define a vector H. The module of this vector will be the inverse of the spacing, the distance between planes, and the direction will be the perpendicular to this family plane. This H vector has three components, H1, H2, H3, called middle index, and is represented with B1, B2, B3 that will be the reciprocal basis. Okay. So I have two spaces, real space and reciprocal space. And both are like the yin yang. They are like the two faces of this coin. I can also formulate what is called a reciprocal metric tensor. And the reciprocal metric tensor will be the outer product of the reciprocal basis vector. It will be this 3 by 3 matrix. Of course, we are not going to calculate, we can do it, but we are not going to calculate the reciprocal metric tensor this way. We just need to know that the reciprocal metric tensor will be the inverse of the metric tensor. Once we know this reciprocal tensor, we can calculate the spacing of family planes, and we can calculate easily angles between planes. This is very important and very interesting. We are going to see that TempServer is this kind of tensors to calculate angles and distance. Also, these metric tensors allow us to go from real to reciprocal and back. So the G vector, the G tensor allow us to go from real space to reciprocal space. And the reciprocal metric tensor allow us to go from reciprocal to real. For instance, I have a unit cell of rutile. Here in yellow is represented the direction 112. This is a direction in the real space. Real space. And we can see that this direction 112 is aligned with the 112 in reciprocal space. And there is a 23 angles between one and the other. If I want to express 1,2 in reciprocal space, that will be the index, the coordinates of this vector. If I want to represent the 112 direction in reciprocal space in the real space, that will be the new coordinates. So in this way, I can go from one space to the other space using the metric tensor. Another important concept will be what's happening when I multiply a vector from the reciprocal space with a vector from the real space. In this case, B and A, because this product will be the identity, just multiply the coordinates of the two vectors, the vector in the reciprocal space by the coordinates of the vector in the real space. In these ways, I can just do this product. And the condition for perpendicularity, it will be very easy because it will be just to be sure that this product is zero. So I can see that if the axis is 110, the family plane 1 minus 1, 1 is perpendicular. I mean, the G vector is perpendicular to this zoom axis, or we can say that this plane is parallel. Plane will be parallel, is aligned with the 110 direction, and the 002 will be also, the vector 002 will be perpendicular to the 10 direction. We say that this family plane will be parallel to the 110. Okay? So this condition is what is called a zoom axis. When I am looking at a crystal in the 110 directions, through this zoom axis, for me, it's going to be very easy to see planes, and all these planes will be perpendicular. The G vector of each plane will be perpendicular to the 110. So it's very important to have this line in order to have a good interpretation of high resolution electron microscopy images. Okay, if you have a question during the talk, you can say that with the hand, and you can raise the hand, and we can answer the question. Otherwise, we can wait for the end of the talk. Okay, another important issue, crystallography is symmetry. We have a space symmetry in a crystal. This is the space group 136. This is a graphical representation of the group. We can see here graphically all the symmetry elements, all the symmetry operations. And here we have 16 operator or 16 equivalent positions. Okay, what can we do this in a computer? In a computer, each equivalent position will be just a matrix, a transformation matrix. So from one position, I can get the other just applying a set of symmetry. Imagine this is the operation minus y plus half. So it will be xy minus y and half. Or here will be x plus half. So it will be 1 here, half here. So its equivalent position can be expressed by a matrix. And using this matrix, we can calculate all the equivalent position to a given one. We can also calculate to a given vector or the equivalent planes to a given plane. So it will be very easy to do this kind of task. And we are going to see that the TempServer is using all these continually. Okay, let's go to the TempServer. There are many software we can use to do crystallography. TempServer is just one of them. So usually when we learn how to use one, all the other will be almost the same thing because we are applying the same concepts in the same idea. This is the one we have developed here, but you can use another one. And this is an online software. And from now on, the software will be accessed through this address. So it will be TempServer.uca.es. So if I go here, I go to the TempServer. So here we have 3 buttons. One is going to be used for the school, for the students when we are learning. This is a global account. This will be an account that is going to be shared worldwide. We can enter here, no problem. And here we have a user login to enter in the TempServer. If you want to have an account to use this software, you can go here to open an account, go to link. So from now on, there will be an application form that you may fill to open an account here. Of course, TEM-UCA global server is intended for use by a group of people. So I will recommend if a group of people to open just one account. In this way, you can share the information, the structures, the model between all the people in the group. So it will be better, it's a more efficient way to work if you have one account for a group of people. And if you want to open an account, I will only ask you to wait at the end of the talk to do that, okay? So if I go here, user login, at the moment, user login, I will put here webinar. Is the account I created for this webinar, and we can enter. When we enter in the TempServer, we are going to see this menu. And the main programs are called Eje Z and Radius. Eje Z come from Eje de Zona, zoom axis, because usually in electron microscopy, we're always dealing with zoom axis. What is the zoom axis? I look in this structure. So this is the origin of the name. During this webinar, we are going to deal mainly with Eje about Radius. If you are interested, in a second seminar, we can focus only on Radius. Okay, let's see Eje Z. So while entering Eje Z, I have a menu like this. So the first thing we need to do is to define a structure, to define a face. How can I do that? Okay, so if I go to edit, I have here several faces. Imagine I want to create a face called Seria. The first thing it's going to ask me is the space group. So I know that Seria is the 225. This information can be seen in many databases and papers. In the asymmetric unit, 2 atoms in the asymmetric unit. So I get now to a form like this. I need to give the dimension of A because it's cubic, only asks me for A. And I will give here the position of the atom. So cerium will be for A. This is the Wyckoff label. It's not necessary to give it, but you know it will be good to have it. It's in 0, 0, 0. Second atom will be oxygen. It's an HC, and it will be O25, O25, O25. Here is the structural occupation factor. By default will be 1. Have one atom in one position. And this is the U-ISO. This is very important if we want to take into account thermal vibration of the atoms in some simulations. If you want to understand what is U-ISO, here, the information here. So the U-ISO in this case will be the average isotropic displacement square. And the unit will be in angstrom square. So here you have some information about this concept that is interesting for some simulation. And here I can put just the reference, okay? When I submit this is just a summary of everything I have given to the program. And when I go to submit again, then the eje theta is run. Here we can see this is the symmetric unit I have given to the program. And this is all the atoms in the unit cell. I have 12 atoms in the unit cell, 12 atoms. Here we have again the 12 atoms in an ordered way. Okay. The program have applied all the operators, symmetry operator of the space group 225. We have 192 operators. After that, from this asymmetric unit, they are created 12 atoms. And here we have the motif. The motif is 1 cerium and 2 oxygen. Because this is an F crystal, we have 4 motifs inside the unit cell. This information is interesting because some programs like DFT programs like Quantum Espresso, we need to give to the programs the motif. We don't give the unit cell. We can give the unit cell we want, but if we want to save time, we don't give the unit cell. We don't give the symmetric unit. The program is asking us the motif of the crystal. Sometimes to calculate the motif is not an easy task, especially when the group is a symmetric group. When it's a symmetric group, sometimes it's difficult to find out the motif. Here, the eje theta has calculated the metric and the reciprocal metric tensor. So we have everything to calculate angles and distance between inside the crystal. Okay, so now we'll go to menu. And when I go to menu, I go to the menu of eje theta. If I want to see what I have created, I just go to view. So in view, I will have here Theria. This is the one I have created. So if I go to the option input, I will see the input data I have given to the program, just the name, the asymmetric unit. If I go to out, I will see the 12 atoms that is in the unit cell. This is the file that is used by Rodius program. That is the second program in TempServer. And if I go to mol, then I am using JSMol to visualize the crystal. Okay, so here I have the crystal, a perfect fluoride structure. This option mol have a lot of buttons here that are very useful. If I go to asymmetric unit, I will see only the asymmetric unit given to the crystal, given to the program. It's cerium and 1 oxygen. If I go to the unit cell, I will see that in the unit cell, when I apply all the symmetry operators, the cerium is repeated 4 times. So I have 4 cerium in the unit cell. And I have, in the oxygen is repeated 8 times. So I have 8 oxygen in the unit cell. So I'm going from a symmetry unit, I apply the symmetry operator, I get the unit cell. Right? This is the true unit cell, because what we have usually or drawing in many books is this image. In this is we have more atoms than in the unit cell, because usually we, by translation, we put all the atoms here, so the image is more beautiful. Okay, this allow us to imagine how will be the crystal, because the crystal, truly speaking, is repeated in space. Okay, so usually this is the normal drawing, but the true unit cell will be just this. This is important to know. Another thing we can do here is we can calculate distance. For instance, if I make a double click on one atom and then the other, I will see the distance between these two atoms, 234 angstrom. So if I choose oxygen and I start to look around in a distance of 225, I don't find anything, of course, because the first neighbor is longer distance. If I go to 250, then the software found these four atoms and they create this polyhedra. So I can easily study polyhedra. And this is the typical image of a fluoride structure that tetrahedral united by the edge. Okay, so there is another way I can study polyhedra. If I choose one oxygen, I can just draw the atoms around. If I use sphere options here, it's here. So it's too much. So maybe I can put here 2.5. I will make the sphere shorter. So now if I choose oxygen and 2.50, I can see the polyhedra in the oxygen. In this way, I can see that this is truly a tetrahedral. Here in the fluoride, maybe this has not too much sense. But if we look in rutile structure, for instance, this is rutile structure, and I choose titanium and the sphere, and then I choose titania and look for the polyhedra, I can see that this polyhedra is an octahedral, but it seems to be a perfect octahedral, but it's not. It's not a perfect octahedral. If I look in this direction, I will see that here, this is not a perfect square. This is just a rectangle. This distance is longer than this one. So of this, the symmetry of this, the C4 symmetry disappear from here. So it will be a different symmetry around titanium. And this can be seen, this is important, because when I see difference in the yield spectra from titanium, from anatase, and from rutile, is due to this distortion from the octahedral. For instance, if I go to anatase here, and I choose this titanium here, of course, if I go to a sphere, I need more atoms. So probably I will choose 3 by 3 by 3, and then a sphere again, and then I can see here the octahedral. If I choose now titanium and draw the polyhedra, I will see that the polyhedra in the case of anatase has a distortion, but distortion now is different from rutile. In the rutile, if I look at this way, I will see a rectangle. Here I can see a perfect square, okay? But if I look at it in this direction, I will see that these four atoms, that they should be in the same plane, now they are not in the same plane. These two oxygen go up. DS2 oxygen go down, and titanium is in the middle. So the distortion of the atoms are different. And this is very interesting later on to interpret some property like Ilse spectra of these species. Okay, what else? Let's go again to Seria. Okay. Here we have also a lot of options here that are very interesting. It's a vector option. So let's draw here a vector like 1, 1, 1. And we're going to put the atoms a little bit smaller. If I go to UVW, I just drawing a vector, 1, 1, 1 vector. If I put here 1, 1, 2, so that will be another vector. Okay. So I can draw any vector in the real space. This is very interesting. Why? Because when I am looking the zoom axis, I am looking the crystal through this vector. So it will be, I am watching the crystal in this direction. So that's why it's interesting to draw vector in real space. But what about reciprocal space? Okay, reciprocal space, in the reciprocal space, you know, we are drawing spatial frequency. The spatial frequency are represented by a family plane. Family plane. Imagine I want to represent the 112 family plane. Okay, so this will be the 112 because this is a plane that is touching one, and touching half because the 2 will be half in C. So this is the 112 plane. We are using here the Miller index. Okay, this is the plane 1, but I have a family plane. So I have infinite planes. So if I go to HKL plus, I will see at least 2 planes. At least 2 planes, but I will have several planes. If I look like this, I will see that I have a lot of planes here. Okay, maybe I can go to rutile to see a little bit better this structure and the planes. If I go to radio a little smaller, and I go maybe to the 112 or 111, so that will be 1 plane, will be 2 planes, that will be another plane, so there will be a family plane. And the distance between 1 plane and the other plane will be this D spacing. I can also represent the G vector. Very small. We can see here a very small vector here because the G vector is really very small. That's why I have put here the option 2 pi G, because this vector is a little bit longer, multiplied by 2 pi. So we can see the vector. We can see that this vector is perpendicular to the family plane. Okay. Here we can see that easily that the 111 directions in real space, it doesn't match the 111 direction in reciprocal space. And this is important to understand that when we are looking at the crystal in the 111 direction rutile, we are not looking at the perpendicular to the 111 plane. Okay. Okay, and now here I have another line with another options here. Why these options are interesting? For this, I'm going to Seria. Imagine I want to draw the 111 plane in Seria. I can see this plane goes through the cation. But imagine I want to see how is a 111 plane for oxygen atoms. Imagine a surface that is ending in the 111 plane of oxygen. And I want to see how is the structure of the oxygen in the surface. So one thing I can do is just click on one oxygen. If I click in one oxygen, here, the coordinates of this oxygen appear. Now to HKL prime, I will see that the plane goes through the oxygen atoms. Maybe I need to have 3 by 3 by 3 unit cell, so I can see how is a full surface of oxygen. I can take the box, the axis, so I can see how is the structure of the oxygen 1,1 surface. I can make a click on one oxygen, and I can, for instance, see if the 1 minus 1 O direction here is. So I can see a direction in the surface. The direction will be the 1 minus 1 O. Or maybe I can go to the -1, -1, 2 direction. Okay, so in this way, I can 3 distance a direction in the surface. This is very interesting when we are looking at the surface. I want to create a model. I have maybe a epitaxial relationship of a surface, and I want to know what distance is in one direction or in another direction. So it will be easier to look at. Okay. So we have seen almost everything here. If I want to see planes, sometimes it's better to see the planes in the crystallography of a plane if we take out the atoms. Sometimes we need the atoms when I am looking at surface, but sometimes it's better to take out the atoms. How can we do? If I go to the option dir comes from direct space. Direct space. If I go to option dir, what I get is the lattice. This is the real lattice. Here I can see just the knots. Some knots appear in blue and other appear in yellow. The not yellow is because this is an F lattice and we have some spots in the middle of the faces. So we have fractional coordinates here. So if I want to see the 1, 1, 1 plane, I can have the 1, 1, 1 plane, and I can see, for instance, I can imagine the smaller region to have something periodic, a square. This is very interesting if I want to do simulation, DFT simulations of a surface, and I want to have the minimum surface possible, but periodic. So this kind of drawing is very interesting for that. So we are drawing, again, we are drawing the real lattice in real space of the crystal. Okay. What about reciprocal lattice? If I go to this, I will see the reciprocal lattice. In this case, I will have this lattice that will be, each spot correspond with a G vector of a family plane, and that will be the reciprocal lattice. Why is it in reciprocal lattice? Because in reciprocal lattice, I can study diffraction very easily. Here I have the wavelength of, by default, will be X-ray. If I go to Ewald, I can draw Ewald sphere in this reciprocal lattice. So the Ewald sphere is a graphical way to represent Bragg law. All the atoms close to the Bragg, to the Ewald sphere, are in Bragg condition. So if I choose Bragg conditions, in this case, any spot are in Bragg conditions or close to Bragg conditions. If I go to 3D and I change direction, maybe I go to the 110 directions and I push Ewald, I will see that the Ewald sphere change because the Ewald sphere with the directions. And now if I go to Bragg, I can see that in this direction, some crystal, some spots are touching the Ewald sphere. If I go to the direction beams, I can see how diffraction is produced. So the beam will be this way. That will be, if the crystal were here, that will be the geometry of diffraction. That will be the geometry of diffraction. So this is very interesting to see how diffraction is happening. Okay, especially usually in X-ray diffraction, what we are doing is just the crystal, rotating the crystal. So if I go rotating the crystal, I am rotating the Ewald sphere. In each direction, we are having different diffraction process. This is what is done in X-ray. Here we are rotating the beam, but usually we are rotating the crystal. What we are doing in electron microscopy, of course, the wavelength will be shorter. This will be about 200 kb. So if I go to the Ewald sphere, I will see that now the Ewald sphere is really, really, really very big compared with our crystal. When I try to go to Bragg conditions, I will see, of course, I have to change here that will be the Ewald sphere. If I go to Bragg condition, I will see that now only the spot in one plane in the reciprocal space are touching the Ewald sphere. That's why, because the Ewald sphere is very, very, very huge. So when I go to beams, I will see how the diffraction is doing. So that will be the beam, the crystal will be here, and I will have diffractions. So in this way, I can see how diffractions is done. If I take everything out, what I am looking at is a plane in reciprocal space. So that will be the reciprocal space, and that will be the plane I am looking at. This is what is called the zero-Laue thumb. The zero-Laue thumb. That will be the first Laue thumb. That will be different Laue thumb. So where we can get some information. But usually we are going to deal with the zero-Laue thumb. One way to go straight to this is just if I wrote here the 110 and I go to this thumb axis. So I will go straight to this plane. Here I can touch, click on the spots, and I can calculate distance and angles. Okay. So one important, so we have everything about real space and reciprocal space. What about phase identification? Okay. When I'm looking at image like this, a high resolution, imagine I'm looking at a high resolution electron microscopy image of titanium dioxide. And the question that arises is this file, is an attached, is brookite? Which zoom axis is I am looking at the structure? Okay, I make a Fourier transform. I can see the spots, the periodicity, the spatial periodicity here, and I can see that almost 4.3, 4.5 angstrom, and almost 90 degrees. It's possible with this information to identify which phase I am looking at and in which zoom axis. Okay, for that, I need to look for all the structure for titanium and oxygen. And here I have the information of rutile, unattached, and brookite. Of course, we have to take into consideration all the phases or the possible phases. If we think we can have another phase, we have to consider that. And we can enter all this information in the eje theta. And here I have unattached, brookite, and rutile. If I go to rutile and I go to HKL, EGZ has calculated all the plane HKL and the D spacing. If I go to UVW, I will have all the possible zoom axes. If I go to the options A and G, I have ordered by angle all the two pairs of planes and the zoom axes they form. So with this map, I can identify, I have a complete map for rutile to try to interpret, to identify the orientation. Of course, it's a task to look for all these planes, so there is a way to do it easily. So I create a group of faces, maybe titanium, let's call this way, and I'm going to put 3 faces here. So one will be rutile, the other one is going to be unattached, and brookite. Okay, so when I have created the group, I go to face ID. I remember it's something like this. Okay. And almost 90. When I go this way, I can see that the only structure possible will be rutile, not unattached, not brookite. So very easily I can see that this image should be rutile in 001 direction. So I go to DDP and I will see the diffraction pattern of rutile in the 001. The first one I get is the kinematical condition. So in kinematical condition, the intensity of the different spots will be proportional to the square of the structure factor. And I can see that some spots have yellow color. This means that in considering the kinematical diffractions, this spot, the intensity should be 0. If I consider, in order to consider dynamical diffractions, it will be better if I go to the advanced mode. If I go to the advanced mode, I can see here the intensity, how it's changing between kinematical, dynamical diffractions considering two beam conditions, dynamical diffraction considering also the excitation vector. Excitation vector is to consider that the Ewald sphere is not a plane, it's an Ewald. So the different spot, there is an error, of the different spots. So I have to consider that. In these 3 conditions, this spot keep yellow, but if I go to multi-beams, multi-beam is because there is interaction not only between this beam and the central beam, because this beam and all the beams around, and I can see that in this case, this spot will get some intensity. And this is what I observe experimentally. Experimentally, I can see this spot. So it's important to do dynamical diffractions because sometimes kinematical diffraction doesn't represent what we are seeing correctly. I want, of course, that will be these last options. I am using the Veth theory, that is an approximation for multi-beam dynamical diffractions, but this is not a full calculation. This is not a full calculation. It's just an approximation. If we want to do full calculation, then we have to do simulations. Okay. And if I want to do simulation, I make a projection of the structure, in one direction. I can do that with projected area. In the projected area, I can see rutile projected in the 001 direction. I can see the diffraction pattern, and I can see the relationship between the image and the diffraction pattern. For instance, if I go to index, I can see that this spot corresponds to the -110, -110. If I go here, -110, I can see this plane, family plane, which is perpendicular to this spot. And the spacing will be the inverse of this amount. Or I can see, just touching here, I can see the spacing will be 325. So in this case, I can see the relationship between the diffraction plane and the planes I see in the projection. If I want to do a simulation, I will recommend to have something periodic in X and Y. For that, I can go to P-cell. So I have a projection of the cell that is periodic in X and Y. In this case, very easy because the unit cell is tetragonal. So if I want to do a simulation of this structure, I can go to the option high resolution electron microscopy. First of all, I had to choose the slide because for multi-slide, this is the theory we are going to use, we need to divide the unit cell in sub-slides. So if I look at the unit cell in this direction, I will see that here I have one layer of atoms and another layer of atoms, and then it's repeated. So it will be good if I divide this unit cell in two sub-slides. So I will choose here two sub-slides, and then I go to high resolution electron microscopy. Okay, and this is an interface to TempSim software by A.J. Kirkland. So it's a basic simulation. Most options are by default. Only you can change several options here. So I am replicating the unit cell. Of course, if I'm replicating the unit cell, I'm going to make a very small simulation. I can do that. Okay, but if I want to see an image larger, it will be good if I replicate this. Maybe I put this 8, 8, and 10. If I put 10 in set, it will means that the length will be C multiplied by 10. So it will be 29 angstrom. Incident crystal, that it will be the resolution. That will be the slide thickness already. And I go here. That will be the exit wave functions. That will be the electronic function at the end of the crystal. Once the electron beam has traveled around the crystal, I will see the final exit wave function. If I go to continue, here I can put all the parameters of the electron microscope, like spherical aberration, the focus, objective aperture, illumination semi-angle, the focus spread. And if I go here, I can have the simulations. So for basic simulation, we can use this. Otherwise, we can download this file, YZ, and I can put this in the software, like this one. So I can work with AutoSlick and later on with image to do the simulation. Okay. Also, we have here two files. One is rutile XYZ and the other one is rutile XTL. This is the format, the file to use MuStem. MuStem allows you to do HADF simulations, but also elemental mapping with EDX and else. Okay. So almost we have done everything. Maybe just to show you that we can export all the data we have in our database in EGZ. We can export all of them in a RAD file. Okay, so that will be interesting to have backup of the we have in our account. And also we have here the option metric to do crystallography, so we can do a scalar product, transformation from real to reciprocal, and vectorial product. Okay, so that will be a review of EGZ software and most of the options we have here. Once we have this information, then we can go to Rodius, and with the information we have, we can create a supercell. What is a supercell? Of course, from a small cell, I can create a big box full of this crystal, and later on, I can create surfaces, and I can create like a nanoparticle. When I have the nanoparticle, I can submit that to simulations. I can simulate particle in perfect axis, tilted. I can simulate single tuning particle, or I can try to simulate supported nanoparticles. I can do any complex thing. And also, we can, using the TEM software, we can even to calculate atomic resolution EELS or EDX mapping, and to match our experimental image with the simulated one. And this is very easy done with Rodius if we know the crystallography of our system. To go deep in Rodius, we can have another seminar maybe after Christmas if you like. So that's it. I would like to thank you everyone for coming and to listen to me. And now if you have any question or any other information, I will be happy to answer you.
Thank you, José Antonio, for your nice presentation. If anybody has any question, they could just raise their hand, and we will give them option to speak. By the way, we will stop now the recording in order to be more freestyle, and anybody can make any question. I see somebody asking question right now.